Hi everybody, welcome to chapter 1.3 part B. We're still evaluating limits analytically, but the main things we're going to talk about today are the dividing out technique, the rationalizing technique, and the squeeze theorem. Now, what I really want the main point of this lesson to be about, and what I want you guys to have your main focus on, is the concept of indeterminate form. That's really the name of the game for this lesson, and we'll go into what that means. But basically, what I would like for you to take away from this lesson is to understand some strategies you can use when you find indeterminate form from direct substitution. Okay, so let's get started. Well, it would help if I started at the beginning of my notes. Give me 1 minute. Okay, so the first topic we'll talk about is functions that agree at all but one point. Functions that agree at all but one point. We have the following definition we can use when we have this scenario in calculus. So, if f of x, f of x, that should be f of x, equals g of x, for all x is not equal to c, so essentially for everything except for one point, except for when x is one thing, and if the limit as x approaches c for g of x exists, then we can conclude the following thing. We can say that the limit as x approaches c for g of x is the same as the limit as x approaches c for f of x. So if we have two functions and they agree for all but one point, if they're the same functions except for one place, then we can say the limit at the second function is the same as the limit of the original. So moving on, let's do an example of this. Say we are asked to find the limit as x approaches 1 for f of x, where f of x equals a piecewise function. So we have x squared plus x plus 1 when x is not equal to 1, and 1 when x does equal 1. Again, that says x squared plus x plus 1. Okay. So what we can do here, following this formula, we know we want to find another function that agrees with f of x for everything but one place. And if just by looking at this, g of x could be made to be just x squared plus x plus 1. Because this function is exactly the same as this piecewise one, except for the one place x is not equal to 1. Or pardon me, except where x is equal to 1. And so we can kind of write out that thought. We can say because f of x equals g of x, for everything, for all, except when x is not equal to 1, then we can say that the limit of this piecewise function, oh goodness gracious, I put that in the wrong place. The limit as x approaches 1 for the function f of x is the same as the limit as x approaches 1 for g of x. So it's the same as x approaches 1 for x squared plus x plus 1. Now we know from our last video that this polynomial is something we can directly substitute into to find our limit. So we can call this 1 squared plus 1, which is just going to be 3. And voila, we've found our limit. You can always double check this graphically, and you can also double check it with your table. So numerically and graphically would be a good way to check this. But it's important to understand that there needs to be, in your f of x graph, there would need to be a hole at x is not equal to 1 for the trinomial, and then you would have a defined point at 1. Okay, moving on. So now let's talk about that indeterminate form. And removable discontinuity. That's a U. There you go. All right, so indeterminate form and removable discontinuity. We're going to start with an example. So say we're asked to find the limit as x approaches -3 for the function x squared plus x minus 6 all over x plus 3. Now, if we use direct substitution, we can see that we would get -3 squared minus 3 minus 6 all over -3 plus 3. And if we did that, if we did this all out, we'd get 9 minus 3 minus 6, which would be 9 minus 9, which would be 0. On the bottom, we'd also have 0. Now, whenever direct substitution yields this 0 over 0, this is called, I want you to write this down, indeterminate form. And let's write about that for a second. What this means is that the limit is not determinable yet. What we must do is divide out common factors, or we can use a rationalizing technique. I also want you to think of indeterminate form as something called removable discontinuity. Right now, there's a point that's going to be discontinuous for this function, but what we can do is we can sort of remove it out and then take the limit of the removed out function. And here's what that means. We'll start with our dividing out technique to demonstrate this. So let's start with the exact same thing. Let's start with that exact same example. Find the limit as x approaches -3 for the function x squared plus x minus 6 all over x plus 3. Okay, but now, given we already know there's going to be indeterminate form from our direct substitution, what we can do is simplify this. F of x, that's a minus 6 at the end, is x squared plus x minus 6 all over x plus 3. Well, we are so good at factoring by now that we can tell this top trinomial can be factored as x plus 3, x minus 2, and on the bottom we still have x plus 3. And check it out, now we get to cross out our top x plus 3 and our bottom x plus 3, and we are left with a new function, x minus 2. So, it's important to note also that we need to state that x can't be equal to 3. Because on the bottom here, before we divided it away, negative 3. X can't equal negative 3. That's what that should say. Let me double check. Yep. Okay, so it should be negative. X is not equal to negative 3 because that would have made this on the bottom here 0, so it would have made it undefined. It's important that we still stipulate that. So now what we can say is that g of x equals x minus 2, where x is not equal to negative 3. And now what we can say is, since this is something that we can directly substitute into easily, since g of x is, we can take the limit as x approaches negative 3 for g of x, which would be negative 3 minus 2, which would be negative 5. And it's important to understand that some calculators won't include a whole at this point. There needs to be a whole at negative 3, negative 5, because our graph, as we talked about, is undefined at negative 3. But sometimes our calculator won't show it, so let's graph it to really illustrate what that means. All right, we'll use the calculators you guys use in class. And if we did, for example, this factored rational expression, we could start by putting a fraction in there. We could press alpha and then y equals and press number 1. And on the top we could say x plus 3, x minus 2, all over x plus 3, and we could graph that. And check it out. We know that there should be a whole right here. We understand that there should be a whole at negative 3, negative 5, but there isn't. So don't let the graph fool you. You need to double check this. We can still confirm with our table and by tracing the point. So we could press second trace, and we want to see what our value is when x equals negative 3, so we're going to press enter, and we're going to type in negative 3. And oh, there's our whole. Do you see how you don't have any y values there? That is what is represented. That's how they're representing that the graph is undefined at negative 3. We could also do that in our table, so we could just get really close to negative 3. So if we press second window and we go to table set, it might be a good idea to start really close to 3, so let's do like 2.999, and then the change in our table we could make 0.001. And if we graph, or pardon me, if we press second and then graph, we can see that, oh, I started in the wrong place. Let's make sure we start at our actual point. We need to start at negative 3, pardon me. So go back to second window, and let's start at negative 2.999. Okay, that'll be closer to what we want. Now press second graph again. Here we go, and we can see clearly in there that at negative 3, there is an error. So the whole is there, it just might not show up in your graph. Okay. let's move on to the rationalizing technique. And we're going to write that right here. Okay, so for example, say that we had the limit as x approaches 0 for the function the square root of x plus 1 minus 1. These are two separate things. This isn't all under the radical. All over x. If we direct substitute, we would get the 0 plus 1 under the radical, or just the square root of 1, which would just be 1 minus 1 all over 0, which would be 0 over 0. And check it out. There's that indeterminate form again, which, remember, indeterminate form just means that there is removable discontinuity. We can essentially always identify whenever we get indeterminate form. That's our red flag that we have more work to do. That basically tells us that we're going to have to manipulate this original function in some way in order to get a new function that we can then take the limit of quickly. All right. So let's talk about how we could simplify this using algebra. We can simplify the numerator if we rationalize it. So remember what that looks like. We still have our f of x, which is radical x plus 1 minus 1, all over x. And we remember rationalizing, or maybe not, that's okay. We'll go over it right now. To rationalize the numerator, we multiply by this whole thing, except we're not going to say minus 1 this time, we're going to say plus 1. So we're going to multiply by radical x plus 1 over radical x plus 1 plus 1. And remember, when we have the same thing on top and bottom, we're really just multiplying by 1, which is definitely okay to do in algebra. And right here across the top, I don't want you to do more work than you have to. Remember the identity. If we have an a minus a b and a plus a b as two factors, we know that's the same thing as saying a squared minus b squared, right? That's that sum and difference pattern. Let's use that to help us. Right now we have an a minus a b, we have an a plus a b. So instead of foiling everything out, let's just make this a squared minus b squared. So on top, I'm going to have radical x plus 1 squared, or just x plus 1, because the squaring would get rid of that radical, minus b squared, so minus 1 squared. Well, 1 times 1 is 1. And on the bottom here, we would still have x outside, radical x plus 1 plus 1. And if we simplified that further, we would get just x, because these 1s would cancel them out. Cancel each other out up here. And then an x over an x would just become the number 1 on top. So if we write all of that simplified out, we get 1 over radical x plus 1 plus 1. And there we have it. Now we have a function that can be directly substituted with the value 0. So let's do that. What we can say is, we need to specify something here. We need to say that x is not equal to 0 because of what we originally started with. We could not have 0 on the bottom. Okay, that's important. That means that we're going to have that hole there at x equals 0. So now we can say, after we did all of that work, we can say that the limit as x approaches 0 for the new function 1 over radical x plus 1 is the same as directly substituting in 1 over square root of 1 plus 1. And again, I didn't write all that out because we know the square root of 1 is just 1. And then 1 plus 1, the bottom would get us 2. So the limit for our new function is 1/2. And again, if you graph it, be careful because the whole might not show up on the graph, but we can always look at our table or we can calculate that value. So let's do that. For our function, let's start with our original. Let's plug that into our y equals. So let's type in the fraction bar first, so alpha y equals, press enter. And we'll do our radical, so we'll press second x squared. And I just pressed second x squared to get that radical. And then we'll type in x plus 1. Now press your right arrow to get out of the radical, and then press minus 1 all over x. Okay. And now if we press second and then window, we want to start our values close to 0. So let's make it maybe negative 0.999. And again, we can have that table change of 0.01. Now we press second graph. We see as we go up to, oh, pardon me, I started at the wrong place. Let's do that. So we'll press second window again. Let's start close to, I don't know why I thought that was close to 0. Pardon me. There we go. Let's do negative 0.001. That will be close to 0. And if we press second graph, there it is. We can even see 0 right there. And we can see clearly that our graph is undefined when x equals 0. There's that hole. Okay, I press second quit. Let's get out of that. And let's go to our next topic. We're going to talk about the squeeze theorem. Squeeze theorem. So write that. Okay. All the squeeze theorem says is the following things. It's sort of like the transitive property of equality that we learned in algebra. So if h of x is less than or equal to f of x is less than or equal to g of x for all x values in an open interval containing C, except at C itself. Okay, so it doesn't have to be there at exactly C. And if the limit as x approaches C for h of x equals L, and also equals the limit as x approaches C for g of x. So basically, if these two, h of x and g of x, share the same limit value at the same C, then we can say that the limit as x approaches that same C value for f of x is also that limit. Okay. I'm going to write down some limits you should know. And I'm not going to go through the proofs of those right now. If you're interested in those, they are in your textbook. The handouts I'll be giving to you in class tomorrow. But in short, what you should know from those proofs is that the limit as x approaches 0 for sine of x over x is going to equal 1. The second one you should know is that the limit as x approaches 0 for 1 minus cosine of x all over x equals, oh, I forgot to write that one down. We'll come back to that in a second. The third one, we'll fill that in. Just write a little box there for now. We'll fill that in. As the limit as x approaches 0 for 1 plus x to the 1 over x equals e. And the value we're filling in for the other one is going to be, bear with me here, zero. Should be 0. Alrighty. And the last sort of thing I'd like to talk to you about is trigonometric functions and indeterminate form. So let's write that. Trigonometric functions and indeterminate, not indeterminate, that's not how you say that, form. There we go. Alrighty, first example of this. So say we were asked to find the limit as x approaches 0 for the function tangent of x over x. This is a case where direct substitution yields, if we fill in 0 and fill in 0, we get 0 over 0. There's that red flag, that indeterminate form, that tells us we need to do some more work before we can actually solve this. So let's do some work. Let's rewrite tangent of x over x as something else. So let's take our function that we're starting with, tangent of x over x, and let's change tangent of x to sine of x over cosine of x, and then we still have that divided by x on the bottom. All right, we're getting somewhere. Remember from complex fractions, all this is saying is that this piece, sine x over cosine x, divided by x, or times 1 over x. So we can say sine of x over cosine of x times 1 over x. And we can rewrite that as sine of x over x times 1 over cosine of x. All right, now we've got some useful pieces. We've done some work, we've rewritten some things. Now let's try to find that limit one more time. The limit as x approaches 0, now for our new function, for sine of x over x times 1 over cosine of x, that can be rewritten as, if we plug in 0 here and here, we actually don't even need to plug in 0 for the first piece, because if you recall, this is one of the limits we should know. Sine of x over x is 1. So we know the first piece is just going to be 1 times, and if we just do some mental math here, we know cosine of 0 is going to be 1, so 1 over 1 is going to be 1. And then we get the answer 1. And again, what we can do here is look at a table numerically to double check ourselves. So let's go back to our y equals and let's put in our original fraction. So let's do alpha y equals. Let's get our fraction in there. We'll do tangent of x all over x. We can now press second window. We know that 0 was that troubling number, right, that we couldn't get close to originally. So let's make our table start close to 0. That's pretty close to 0. That's going to get us really, really close. So now let's press second table and check it out. There we go. The limit as x approaches 0, we can see is clearly 1, right, from both sides. If we put that 0 in the middle, we can see from both directions that we are definitely approaching 1. And there it is, even if our graph doesn't show it, our table is telling us that there's that hole, that error when x equals 0. Fabulous. Okay, that is everything I have to show you. We'll see you in class tomorrow.